Okay, so continuing with section 2.2, I'd like to talk about piecewise functions next. A piecewise function is two or more functions that are spliced together to form a new function. Splicing, if you're not familiar with what that term means, the only instance that I can think of that would really be relevant to what we're about to do is when you, at least in the old days when movies were on film in the movie theater, is that sometimes you would have, like if the film got garbled or something, you'd have to cut out a little piece of it. And so you'd snip out the part that was bad, and then you would take the two ends and tape them together, and that was called splicing the film. So you tape one side to the other side, and that's called splicing. So that's the way you want to think of this. We're going to cut two functions in half, and then we're going to take the half of one and splice it to half of the other, and we're going to tape them together. That's really what a piecewise function is. All right, so here's an example of what the graph of a piecewise function might look like. The two graphs that are being spliced together here are just horizontal lines which have very simple equations that describe them. I think sometimes maybe a little too simple, that students have a little bit of trouble with it because of how simple the equation looks. But horizontal lines are described with the equation y equals some number. All right, so what we would like to be able to do is take a graph like this where we have half of one graph, half of one horizontal line spliced or taped together with half of another one, and come up with a way of describing that as an equation. And there's quite a lot of different pieces of information that have to go into doing that. So for example, we have to recognize where the graphs are being taped together. In this case, they're being taped together along this vertical line here, which I've drawn for you in red. To the left of this vertical line, we have a graph which can be described by the equation y equals -1. But that equation is only valid to the left of this red line. That's the only place where that graph exists. And so that horizontal line there, the y coordinate's always -1, and so the equation is just y equals -1 for that graph. To the right of this vertical line, we have a different horizontal line which can be described by the equation y equals +2. Right? That horizontal line, every point on that horizontal line has a y coordinate of +2. Okay. How do we describe these different regions? So we have a region to the left of the vertical line, a region to the right. Well, that vertical line is actually where x is equal to -1. So again, the vertical line can be described by the equation x equals -1 because that's what every x coordinate has to be on that vertical line. So to the left of that vertical line is x values that are smaller, right? So as you go to the left, the x coordinates get smaller, and so we can describe the region to the left of that vertical line as where the x coordinates are less than -1. So we're using the equation y equals -1 where the x coordinates are less than -1, right? On the vertical line itself is where x exactly equals -1, and to the right of the vertical line is the region where x is greater than -1. So if you move to the right of that vertical line, all the x coordinates in that region to the right are bigger than -1. So that's how we can describe those two different regions. And so we have to take all this information, the two different equations that are being graphed, the regions in which they're being graphed, x less than -1 and x greater than -1. We also have to denote on the vertical line where x is exactly equal to -1, which graph should be used, and that was indicated, I covered it up with my red line there, but it was indicated with an open circle versus a closed circle. So where you see the closed circle, that point is actually included on the graph. And so we're including the endpoint from the graph on the left-hand side where y is equal to -1. So that point gets included. We do not include the endpoint from the graph on the right where y is equal to 2. And so that also needs to be indicated in our equation that we're about to construct. So what I'm about to show you is going to look really complicated, but I think you'll appreciate that it provides quite a lot of information in a nice compact form. So this is what it's going to look like. Okay, oh sorry, so I skipped ahead of myself there. So because we have the closed circle on the graph on the left-hand side, we want to describe that region with an equals to. So x could be less than or equal to -1 for the graph on the left-hand side. Right, and so here's what the equation has to look like. So all together, putting all the information together, it looks like this. We use a curly brace, and so because we have y equals in both equations, we don't need to repeat that. So we just write it one time. y equals, and then with a curly brace, we're going to split it out and describe the two different equations that are involved. We have in one case y equals -1. We put that one on top. It doesn't really matter where you put it, but we put it on top this time. And on the bottom, we have the equation y equals 2, right? But the y equals part just gets written once for both of those. And then for each of those equations, y equals -1 and y equals 2, we have to describe where the equation is being used. So we use y equals -1 for x coordinates that are less than or equal to -1. And we use y equals 2 for x coordinates that are greater than -1. So all of that information gets put into that format. And so that's the way we write our piecewise functions. You'll also find, because we're using function notation more heavily in this course, that instead of calling it y equals, they'll use f of x instead. So I'm going to make the same substitution here. But again, the y variable is f of x. It's the same thing. All right, so that's how you can translate, or I shouldn't say translate maybe, but that's how you can describe a piecewise graph as an equation or as a function. And that might be some of your homework. So you want to make sure you know how to do that. The other direction is going to be more common. So the other direction is being given a piecewise function and graphing it, right? So in the previous example, we were given the graph and we discovered the equation. In this case, we're being given the piecewise equation and we're going to try to draw the graph based on the equation. So again, we have to pick out all that information. It's all packaged up into that nice, neat format. We have to unpackage it to figure out what this graph is supposed to look like. So first, I'll start by putting my Cartesian coordinate system down, and I've labeled the numbers here. The next thing you want to decide is where you're going to be switching from one equation to the other in your graph. And that's pretty easy to see if you look at the equation, that when x is less than -1, we're using one particular equation, y equals 2. And when x is greater than or equal to -1, we're going to use the other one. So where is it going to switch at? It's going to switch at x equals -1, just like the previous example we were looking at, right? And so what I'm going to do is draw the vertical line that represents x equals -1, because that is the vertical line where we will switch from one equation to the other. Right? So I'm going to draw that right there. Right? So this is my preferred method. Technically, that vertical line doesn't exist in the graph, but I still like to draw it there so I can see that, so I can know where I'm switching from one equation to the next. Right? And so by drawing this vertical line, it's going to split my Cartesian coordinate system into two regions. The region to the left is where the x coordinates are less than -1, just like in the last example. The region to the right is where the x coordinates are greater than -1. Right? So let's go ahead and start with x less than -1. That region, we can see that being described for the top equation. Right? So the arrow is pointing to the condition where it says x is less than -1. That applies to that top equation. That top equation is y equals 2. Right? Again, f of x is the y variable. Right, so we're in the region where x is less than -1, we want to use that equation, f of x equals 2, which you can just think of as y equals 2, because f of x is your y variable. So I want to graph that equation, y equals 2, in that region where x is less than -1. Y equals 2, again, it's a very simple equation, and it's describing a horizontal line on y equals 2, on the, I don't want to say it passes through the y-axis at y equals 2, because it can't reach the y-axis in that region, but it's where all the y coordinates are equal to 2. It's the horizontal line where all the y coordinates are equal to 2, which is right here. All right, so it's this red line right here. And we graph that horizontal line starting from the left-hand side all the way up to that divider, that vertical blue divider that I've drawn, because that's where we have to stop using that equation. So we use y equals 2 only up until we hit that blue line, and then we have to stop drawing it. So on the other side, on the right-hand side, where x is greater than -1, what equation do we want to use? We want to use the second equation, f of x equals -2. Right? So on the region on the right, we have x is greater than -1. And if we look at our equation, the equation tells us to use the equation f of x equals -2 for that region. Again, f of x equals -2, you can think of as just y equals -2, right? F of x is the y variable. So we want to graph the equation y equals -2 in that region where x is greater than -1. Y equals -2, again, is just a horizontal line where all the y coordinates are -2, which is found right here. Right, so there's the horizontal line, y equals -2. Again, we start from the right-hand side and we draw all the way to the left until we hit that blue divider line, and that's where we have to stop drawing that equation. It's only allowed to go that far, and then we stop using it at that point. And so we're pretty close to having our piecewise function. The last remaining question is, what do we do when x is actually equal to -1? So on the blue line itself, which point should get filled in and which one should be an open circle? We can't have them both filled in because then it wouldn't be a function. It wouldn't pass the vertical line test in that case. So we have to have one open circle, one closed circle. Which one should be which? You have to go look at your equation, and wherever you have the equals to in the conditions, that's where you want to use the closed circle. Right, and so we have the equals to for the bottom equation, right? X is greater than or equal to -1 for the bottom equation, which is the equation that we graphed on the right-hand side. So that is where we want to use our closed circle, which means the other graph for the equation on the left-hand side, we use the open circle. Right, and so there's the graph. That is the graph that is being described by that piecewise function. So let me erase all the stuff around it so that you can just look at the graph, because I know I made a big mess on the screen with all the math that we were doing, but there's the graph right there. You might be asked to find the domain and range. The domain, again, is how far to the left the graph goes, how far to the right it goes, and in this case, it's going forever to the left and forever to the right. And so the domain will be -infinity to infinity, right? And any value of x is allowed on this graph. You can, for whatever x coordinate you want to pick, you can find a point on this graph with that particular x coordinate. So the domain is all real numbers. The range is how far down the graph goes and how far up it goes. And this one's really unusual because it doesn't go down forever, it doesn't go up forever. In fact, it's actually mostly flat, and there's only two different y coordinates that you can possibly have on this graph. So remember, the range is what is it possible for y to equal, and in this case, there's only two values that y could possibly equal. So we don't even want to use an interval, right? We use an interval when there's a range of numbers, like -infinity to infinity. That's everything in between. But for the range, there is no in between. It's just -2 and +2, and that's it. So the way we describe that is using the set notation, the curly brackets there. And so the range is just the numbers -2 and +2 and nothing else, not even in between those two values. Okay, let's try another piecewise function. This one's going to be a little more complicated in the graphing, but we'll approach it the same way. First, we'll set up our Cartesian coordinate system, and the first thing I like to identify when I'm doing a piecewise function is where is it going to switch from one equation to the next. And if you look at the equation, it appears it will be switching at x equals 1. Right, when x is greater than 1, we're going to use the equation y equals x plus 1. And when x is less than 1, we're going to use the equation y equals x minus 3. So at x equals 1, it's going to be switching from one equation to the next. And so I mark that on my Cartesian coordinate system as a vertical line. I like to make it a dotted vertical line because technically it's not really part of the graph. It's supposed to be an invisible line, but it's an invisible barrier that I like to draw in so I can actually see it. So this time it's a little bit different than the last couple of examples we looked at. The area to the left of this vertical line is where the x coordinates are less than +1. Right? So anything to the left of that vertical line will have an x coordinate that's less than 1. So that's how we describe that region to the left. And any point to the right of that vertical line will have an x coordinate bigger than 1. So that's how we describe that region. X is greater than 1. All right, so we're going to jump into actually graphing this. Sorry, I had more on the screen than I anticipated I would at that time. So let's start with the region on the left-hand side. That's the region where x is less than 1. Let's find that condition in the equation. It's the condition for the bottom equation. So we want to use the bottom equation when x is less than 1. So sometimes I'll switch that up on you, so be careful about that. So the bottom equation is the equation y equals x minus 3. So I want to graph the equation y equals x minus 3 in the region to the left of the blue vertical line. To graph this equation, y equals x minus 3, don't forget what we learned in chapter 1. It's a linear equation, and we can use the slope and the y-intercept to graph this equation. So the slope of this equation is m equals 1, right? The slope is 1. And the y-intercept is at 0, -3. We just picked that stuff, we picked that information right out of the equation. And so I'll go ahead and graph the y-intercept, which is at 0, -3. So you see the orange dot there. The slope is 1, so that tells me what I'm going to do is I'm going to go up 1 and to the right 1, which actually carries me right up against that blue divider line. And we will need to be careful whether we want to use open circle or closed circle. But if you'll look at the condition, we actually, for this equation, it's x is less than or equal to 1. And so since we have the equals 2 in that condition, we actually want to use the closed dot on this graph. So it'll work out fine just leaving it as a closed dot. But there I have 2 points, the y-intercept, 0, -3, and that second point that I get when I use the slope, And so with 2 points, we can graph the line. We just connect those 2 points with a straight line. But what you need to be careful about is that you don't go past that invisible barrier, right? That vertical blue line is an impassable barrier for this graph. The graph should not pass that vertical blue line. It has to be in just the region on the left-hand side. So only where x is less than 1 are we allowed to have this equation y equals x minus 3. We can't go past the vertical line. All right, so that's the graph on the left-hand side of that vertical line. What about the graph on the right-hand side of that vertical line? Well, that's the region where x is greater than 1. And if we look at the equation, that condition matches up to the equation y equals x plus 1. Or, it matches up with f of x equals x plus 1. But again, f of x is just the y variable. So for the region on the right-hand side, we want to graph the equation y equals x plus 1. Again, it's just a linear equation. And we can use the slope to help us graph this. The slope, again, is equal to 1. But the y-intercept is going to be a problem. So you'll notice at the bottom I made a note. In that region, if I have to stay to the right of that blue line when I'm graphing this equation, and if I can't go any further to the left, I can't use the y-axis. The y-axis is cut off for me in this case. So for the region on the right-hand side, I cannot use the y-intercept because I don't have access to the y-axis. So we'll have to think of another way of graphing this equation since we can't use the y-intercept. Another way of graphing a linear equation is just to get 2 points. Any 2 random points will do, because once you get 2 points, you can graph your line. So instead of using the y-intercept, I'll just have to find some other points to use. So I'm going to make a chart. I'll pick a couple of values for x, but make sure you're following that condition. We can only choose values of x that are bigger than 1 if we're going to use this equation. So I'm going to choose x equals 2, and I'll choose x equals 3. Those are the easiest ones to choose that satisfy that condition. Right, so choosing x equals 2, we plug that into the equation. We get 2 plus 1, which will be 3. So y is equal to 3. And choosing x equals 3, we plug that into the equation. We'll get 3 plus 1, which is 4. So I get y is equal to 4. And so that gives me a couple of points that I can graph. So that gives me the point 2, comma 3. And it gives me the point 3, comma 4. I plot both of those points. And now I have 2 points in the region on the right. And I connect those 2 points using a straight line. This is a very common answer that I will get from students on quizzes and tests, but it's not quite correct because this equation, this graph, should go all the way up to that blue vertical line. And we're stopping a little bit short there. So you'll notice there's a little gap right there between the end of the graph and that barrier that we're supposed to reach. And so we need to make sure we continue that line all the way to the barrier. So it should look like this. So there shouldn't be any gaps there. We should go straight from the graph on the left-hand side to the graph on the right-hand side, and there shouldn't be any gaps in jumping from one. I mean, there's a gap vertically, but there shouldn't be a gap horizontally. For this particular graph on the barrier, we should use an open circle, right? We already decided to use the closed circle for the graph on the bottom, so we're going to use an open circle up here. Right? And again, we do that because there is no equals to on the condition for this particular equation. And so there's our graph for this piecewise function. I'll erase all the work that we just did so you can just look at what the graph looks like. You may be asked to find the domain and range. The domain, again, is how far to the left the graph goes, how far to the right. And again, in this case, the graph goes forever to the left and forever to the right. So the domain is negative infinity to infinity. The range is how far down the graph goes and how far up it goes. And it will go down forever. So it goes down to negative infinity. It goes up forever, so it goes up to positive infinity. But that doesn't quite accurately describe all the possible values for y. There are certain values for y that do not occur on this graph. For example, y equals 1. There is no point on this graph where y is equal to 1. Right? Here's where y is equal to 1, and that just doesn't exist on the graph anywhere. So it shouldn't be in our range. So if we left our range as negative infinity to infinity, it would be a little bit misleading because there are certain values of y right in here that do not occur on the graph. So what we need to do is take into account this vertical gap that I mentioned earlier. It does go down forever, so let's start from there. It goes down to negative infinity. Starting from negative infinity and coming back up, we have to stop at y equals negative 2, right? That's where the graph stops for a moment. So we have to pause at y equals negative 2, including negative 2, so we use a bracket. And then we jump from there up to y equals positive 2. So we need to do a union and start a new interval starting at positive 2, but not including the 2. So we use a parentheses here because y equals 2 is not included here. But that's where we're going to start from. And then from there it goes up forever. So we're starting at negative infinity. It goes up to y equals -2. We pause there, we have a gap, and then we pick back up again at +2, and then from there we go up to infinity. So this is what the range is. All right, the last topic in this section is increasing, decreasing, and constant. So here's the definition. I'll just read it to you and then we'll talk about what it means. If, as x increases on a given interval, y also increases, then we say the function is increasing on that interval. If y remains unchanged, then we say that the function is constant on that interval. If, however, y is decreasing, then we say that the function is decreasing on that interval. All right, so that's some pretty technical language there, and this is bordering on the kind of language that you would see in a calculus class. So let me explain what all this means. As x increases, all that means is that the graph is going from left to right. So from wherever you're at on the graph, if you head towards the right, your x coordinates will be increasing. So as x increases just means you need to be going from left to right as you're looking at your graph. If the y also increases, well, what does the graph do if y is increasing? The graph is going up. So if, as you're going from left to right, the graph is heading up, you have an increasing part of the graph, right? That part of the graph happens to be increasing. If y is decreasing, well, what does the graph look like if the y coordinates are getting smaller? The graph is going down. So if, as you're going from left to right, the graph is heading down, the graph is decreasing at that point, or on that interval. And if the y remains unchanged, what does that graph look like? If the y coordinates aren't changing, we have a horizontal line. The graph will be flat, and so if the graph is flat, it is constant on that interval. All right, so that's how you interpret that. You need to be going from left to right, and you look to see if the graph is going up or down or staying flat. All right, so let's take a look at an example. So here we have a parabola. This is from the square family of functions, which we'll talk about in section 2.3. And so when we look at this graph, our eyes are probably immediately drawn to the middle of the graph. So if we look at the middle of the graph, it looks like it's going up to the left and it's going up to the right, but that is not how we decide the increasing and decreasing and constant. It's very important that we look at the graph as x is increasing, meaning we have to be looking at it starting from the very left-hand side and looking towards the right. So you want to put your eyeball over here on the left-hand side of the graph. So make sure you're starting from the very left-hand side. So this is where you begin. And from the very left-hand side, as we look to the right, we see that the graph is going down. Right? So we're looking towards the right. For a while, we don't see the graph at all, but as soon as it comes into view, we see that it's heading down. So the graph is decreasing to begin with. Right? And since we're starting from the very left-hand side, we're starting from -infinity, and the graph is decreasing until we reach this point right here at the very bottom. That's where it stops decreasing. And what we want to pick out from that is the x-coordinate at which it stops decreasing. So we would say it stops decreasing where x is equal to 3. So we'll see this in just a minute. I'm sure I have it on the screen in just a moment. So it's decreasing from -infinity, as I mentioned a moment ago, because we're starting from the very left-hand side, until we reach x equals 3. Right? And so that's what we're going to put there. Now, theoretically, there should not be a bracket on the 3 for this particular problem, but your online homework system, if you're in my class, requires you to use a bracket on this 3. But if you take calculus, they will say, no, it's not actually decreasing at 3, so you should use a parenthesis. So there's a little bit of a discrepancy there. So I'm going to put a bracket because that's what will be right for the homework system that we are using. Okay, so then what does it do once it hits that point? Once it hits x equals 3, the graph begins to pick up. It heads in the north direction. So there's where it's decreasing. Starting from this point, it starts increasing. So it's increasing starting at x equals 3. So beginning at that point where we left off on the decreasing version of the side of the graph. Excuse me, I'm getting my words jumbled. So starting at x equals 3, the graph begins to increase. So this is where we're going to start our interval. And it continues to increase forever as we head to the right. And so that's until infinity. All right, so it's increasing from 3 to infinity. It's decreasing from -infinity to 3. Make sure you're using the x coordinates when you're describing the increasing and decreasing. All right, let's try another one. All right, so here's an interesting looking graph. Again, it looks like you have parts going down and parts going up, but actually this graph, once we analyze it correctly, we will realize it never decreases. It's always increasing or constant. So again, we have to make sure we start from the very left-hand side of our graph. So we're starting from -infinity. As we look to the right, we see that the graph is actually going up. Right, so we're starting from negative infinity, and as we do that, from the left-hand side, we see the graph is going up. So we say the graph is actually increasing at first until it reaches this point here at -5, right? And we want to use the x-coordinate there. Now the y-coordinate is 1, but we don't want to use the y-coordinate, and you don't want to put a point there. So I have a lot of students on the test that will say negative infinity, comma, -5, comma 1. You can't throw in a point there. You have to make a choice, and you want to use the x-coordinate to describe this interval. So it's going to increase from negative infinity to -5. Again, we're going to use brackets, even though that's not technically correct. Right. Now, starting at -5, what does the graph begin to do? It goes flat, and so we have a constant interval here. It's constant from -5 until we reach this point here, which has an x-coordinate of 10. And so it's constant from -5 until 10. And then starting at 10, what does it do? It picks up again. It goes up. And so it's increasing from 10 to infinity. And so because we have two different intervals on which it's increasing, we will use a union symbol between the two intervals. So there is our final answer. In section 2.3, we'll be looking at transformations of graphs. In order to use the technique of transformations for graphing, you have to memorize some basic graphs for different types of equations. So I'm going to go through these quickly, but you want to make sure you memorize the shape of the graph. And another helpful thing to remember for these graphs is that they all contain the point 0, comma 0, the origin. That will be helpful when we start doing some problems. All right, so the first family we're looking at here is the absolute value family of functions. The basic equation is f of x equals the absolute value of x. That's the most basic absolute value equation that you can have of two variables. And the basic graph for that equation is a v-shape where the pointy end of that v-shape is at 0, comma 0. All right, so you want to make sure you memorize that. The next family we want to look at is the square root family of functions. The most basic equation in that family is f of x equals the square root of x. And the basic shape for that graph is this sideways parabola. It's half of a sideways parabola. Again, the graph contains the point 0, 0. In this case, it actually begins at 0, comma 0. All right, so you want to memorize that shape for that type of equation, square root equation. We also have the square family of functions. So the basic equation for that family is f of x equals x squared. That's the most basic equation. That would be a square function. And the basic shape of this graph is a full parabola. It's an upright, not a sideways parabola, but a regular upright parabola. And it also passes through the point 0, 0. The basic one does. The basic graph does. All right. So you want to memorize that graph as well. Excuse me. And then the cube family of functions. Here's the basic equation. It's f of x equals x to the third power, and the basic graph looks like this. It's I don't know how you would describe it, but it does contain the point 0, 0. It's a completely increasing graph, so it starts on the left-hand side at the bottom, and it just goes up from there, and it kind of tapers off for a moment before increasing again. All right, so you want to make sure you memorize these basic graphs. There are three different types of transformations that you need to know. The first one is called translations. The second one is called reflections. And the third one is called stretching or shrinking. The third one is pretty self-explanatory. It's taking the graph and stretching it or shrinking it. You might imagine what this, what's the analogy for this would be, minimizing or, enlarging a picture on the computer or shrinking it down. The basic image of your picture looks the same, but you can stretch it out to make it bigger, or you can shrink it down to make it smaller when you're working with it on the computer. So that's the same idea with the stretching and shrinking of your graph. You can enlarge it, you can minimize it, you can shrink it down, but the basic shape of the graph will stay the same. The other two are a little more technical in their terminology, so let me explain what these mean. Translations is shifting the graph either vertically or horizontally or both. So just moving it, basically. That's what a translation is. It's a fancy way for saying moving the graph from here at this part of the Cartesian coordinate system to another part of the Cartesian coordinate system. You don't stretch it or shrink it. You don't do anything else to it. It's like copy and paste. You copy it from one location and you paste it to another location. That's what a translation does. The other one, reflection, is simply flipping the graph over. So if you want to do a reflection of the graph, you flip it over. The major question is, in what way do you flip it over? You could flip it over the x-axis, you could flip it over the y-axis, you could flip it over some diagonal line. There's many ways you can rotate, or not rotate, but flip a graph over. And so you want to make sure you determine that first before you, flip it over. You have to figure out which way do you want to flip it over. Thankfully for this class, we are only studying one type of reflection, so you won't have to memorize the different ones and when you do which. There's only going to be one. All right, so let's go ahead and take a look at the translations first. So the graph of y equals f of x plus k is a vertical translation of the graph of just f of x by k units. So a vertical translation means you're going to move the graph up or down by k units. The graph that you move up or down is whatever f of x is, which presumably will be one of our basic equations that we were looking at just a moment ago. How do you know which way to go? How do you know whether it should be shifted up or down? Here's how you tell. If k is positive, so you see the k there, the plus k next to the f of x, if that value is greater than 0, which is just a mathematical way of saying if that value is positive, then the graph is shifted up by k units. If k is less than 0, then the graph is shifted down by k units. So that's how you will determine whether you shift it up or down. As I mentioned just a moment ago, k greater than 0 is the same thing as saying that you want k to be positive. And again, if k is positive, you want to shift it up. K less than 0 means you want k to be negative. Not that you want it to be negative, but if k is negative, you need to shift the graph down by whatever that number is, whatever k is equal to. All right, we'll look at an example here in just a moment, but before we do an example, let's talk about the horizontal translations. So the graph of y equals f of x minus h is a horizontal translation of the graph of f of x by h units. So notice what's different in this case is that the h is right next to the x variable, right? Whereas in the previous definition for vertical translation, the k we were looking at was just tacked on to the end of whatever function or equation you were looking at. This is different. The h is embedded directly into the equation right next to where the x variable is located. So if it's a square root equation, for example, this number would be right inside the square root with the x. If it's an absolute value, this number would be right inside the absolute value. Whereas k in the previous definition is outside the absolute value, or it's outside the square root. So that's how you'll tell the difference between vertical and horizontal translations. Just like in the previous case, if h is greater than 0, the graph will be shifted in the positive direction. It'll be shifted to the right by h units. And if h is less than 0, the graph is shifted to the left by h units. I should have mentioned at the beginning when I started reading this definition that horizontal means left or right. So as I mentioned a moment ago, if h is greater than 0, that means if h is positive, right? That's just a mathematical way of saying positive. We shift it to the right, which is the positive direction on the x-axis. If h is less than 0, that's just a fancy way of saying if h is negative, it gets shifted to the left. Right? So it's the same as with k, except that the trick with this one is that inside that function, we have x minus h. There's a minus sign in front of our value of h. So if h is actually positive, then, so if h is actually positive here, then we will have x minus some positive number, and so our equation will have x minus something. If h is actually negative, then what we'll have in our equation is x minus some negative number, which will look like x plus a number, right? Minus a negative becomes plus, and that's what we would see in our equation. So in the equation, it will actually look backwards. If h is positive, you're going to have a minus going on in your equation. And if h is negative, you're going to have a plus going on in your equation. So we have to kind of keep that in mind while we're trying to interpret this. So let's go ahead and take a look at an example. We have the equation y equals the absolute value of x plus 2 minus 3. So I'm going to write that again to make it a little bit bigger. And so the first thing you need to recognize with this example is that it's an absolute value function, right? We have x inside of an absolute value. So this belongs to the absolute value family. And so let's acknowledge that to begin with. And as soon as you acknowledge that, you should then consider, well, what's the shape of this graph and what's the most basic equation for this family? We want to start with the most basic equation and we're going to build up from there. So the most basic equation for the absolute value family is f of x equals the absolute value of x. And so we have that equation memorized for the absolute value family. That's the most basic one. And we have the graph memorized for that basic equation. So for that basic equation, the graph is a V shape where the pointy end of that V shape is at 0, 0. Now that's the graph of just absolute value of x. We want to get the graph of the absolute value of x plus 2 minus 3. And there's some differences in those two equations. And each of those differences will have an effect on the graph, on the basic shape of the graph. Right? And so here are the two things that are different between the basic equation and the equation that we're trying to graph. We have a plus 2 inside the absolute value directly on x, and we have a minus 3 outside the absolute value. Each of these two numbers will have an effect on the graph. What effect will they have? Well, the plus 2, I usually like to start, even though I mentioned this one last in the definitions, I like to start with this one first. The plus 2 is directly on the x variable, and so that's going to be a horizontal translation. It will shift the graph either left or right, and we have to decide which way it should go. And like I said, for the horizontal ones, it's sort of backwards from what you might expect. The x plus 2 actually means that h is a negative value. H is actually negative 2 in that case. And so we're going to shift the graph to the left by 2 units. All right, so the plus 2 is actually going to take that basic graph that we have there, the V shape, and shift it to the left 2. The minus 3 is going to have the effect of shifting the graph down by 3 units. And so we can do both of these at the same time. There's no reason that we have to do one first and then the other. We're going to do both. We're going to take this V shape, shift it to the left 2 and down 3. Every single point on that graph will go through the same translations. They'll all get shifted to the left 2 and down 3. But what I like to do is I like to track one particular point through that translation, and then I just copy the rest of the graph along with that one point. And the one point that I like to track is this point here at 0, 0. So we're going to take that point, shift it to the left 2, and then down 3. And so the point will end up here at this location, -2, -3. The rest of the V shape will tag along and end up in the same spot relative to the red point that I have marked here. So the rest of the graph will look like this. Right? The V shape just tags right along with that particular point. And so this is what our graph looks like. So the red graph that you see here is the graph essentially of the equation that we were given at the beginning, y equals the absolute value of x plus 2 minus 3. The only thing that we can do to try to improve this graph, because we have the right shape, we have it in the right spot, the only thing we can really do to improve this graph is to plot a couple of points from the original equation just to make sure we have it nailed down and as accurate as we can possibly get it. So let's go ahead and set up a chart here, and we'll just pick a couple values of x. We don't need to pick -2 because we already have that particular point. All right, so we don't need to choose x equals -2 because we already have that point. So let's pick something else. Let's pick one point to the left of that value and one point to the right of that value. So I'm going to pick, for my values of x, I'm going to pick 0 and -3. 0 would be to the right of the point that I already know, and -3 would be to the left of the point I already know. And I'm not going to go through the details of this, but what I'm going to do is plug it into that equation. You know, each value of x, I'll do one at a time. So I'm going to plug in x equals 0 into that equation, and I'll get y is equal to -1 when I simplify it. And then I'll do the same thing with x equals -3. I'll plug it into that equation, and when I simplify it, I'm going to get y is equal to -2. And so I can take these 2 points, plot those, make sure that my graph actually goes through those 2 points as well. And because the V shape is a straight line to the right and a straight line to the left, this should nail down those straight lines perfectly. So turns out that I was careful enough in how I drew my original graph that it already went through those points. But other times I have to erase the original graph I have there so that it will go through the points that I need it to go through. So you might need to erase and redraw it. All right, so there's our graph. So the red line you see there is the graph of the equation. Let me go ahead and just redraw that over here to see so there's not a big mess going on around it. And so there's the graph right there. Something else you might be asked to do is find the domain and range of the graph. So remember, the domain of a graph is how far to the left does the graph go, how far to the right does it go. In this case, it goes forever to the left and forever to the right. So the domain will be -infinity to infinity. The range is how far down the graph goes and how far up it goes. And so in this case, how far down the graph goes, well, it's limited. It doesn't go down forever. It actually only goes down as far as -3 on the y-axis. Right, so that point there, -2, -3, is the bottom of that V shape. And we want the y-coordinate of that point for the range. So we take -3. How far up does it go? It goes up forever. It goes up to infinity. The next type of transformation is called a reflection. And so here's the definition that you need to know for this. The graph of y equals -f of x is a reflection about the x-axis of the graph of f of x. So again, presumably f of x will be one of your basic functions. And what makes the equation we're looking at in the definition different is that there is a negative sign in front of the f of x. So if you have a negative sign in front of your equation, that is a reflection about the x-axis. And what that means is that the graph is flipped over the x-axis. That's what reflection means. So you just flip it over the x-axis, and that's how you get your new graph. Well, let's take a look at an example. We have y equals -square root of x. So again, if we're going to use this technique of transformations for graphing, we first have to identify what family of functions we're dealing with here. And in this case, we're dealing with the square root family. And so as soon as you realize it's the square root family, you should immediately think of the basic equation in that family, which is f of x equals the square root of x. And you think of that one because it's a really basic one that's easy to build off of, and you have the graph memorized for this equation. So the basic graph of the square root of x is this particular shape. All right, it's the square root graph. It's half a parabola going sideways. And so that's where we're going to start from. And again, so we compare our basic equation with the equation that we were given, and the only difference between the two is the negative sign in front of the square root of x. And the effect that that will have on the graph is it will flip it over the x-axis, and that's the only change we need to make. So if we take the blue graph that you see there and we rotate it about the x-axis to flip it over, what we will get is the green graph. Right, so this negative sign in front of the square root is a reflection about the x-axis. If we flip it over the x-axis, this is what it looks like, the green graph that you see there. All right, again, what we could do to ensure more accuracy of our graph, because this is essentially the right graph, we have the right shape in the right place, but we want to make sure it's as accurate as possible, so we graph a couple of points. Again, I'll choose some that we don't already know. The only one that we do know right now is that point at 0, 0 is still there. But let's pick some other points that are going to be to the right. There will be no points to the left. There's no negative values of x, because if you try to pick a negative value for x, you'll just get an imaginary number, and it can't show up on the graph here because the Cartesian coordinate system doesn't have a place for imaginary numbers. So we'll pick some easy ones. Again, knowing that it's going to go in the square root, we should pick numbers that we can easily take the square root of. So I choose 1 and I choose 4. We plug these numbers in one at a time into this equation and find the corresponding value for y. So we'll find when we do that we get -1 for y when we plug in x equals 1, and we'll get -2 for y when we plug in x equals 4. So this gives us a couple of points that we can graph, and it might be a little bit off the window there, but you'll see it on the next screen in just a second. But I go ahead and plot these 2 points, and again, I drew my graph carefully enough so that I didn't have to erase and redraw it. But if your original green graph is off the mark a little bit, you go ahead and plot these points, you redraw that graph to get it as accurate as possible. Right, so here's what your graph looks like. These are the points that we know. We already knew 0, 0. We have 1, -1, and also 4, -2. And we connect those points in the shape that we were expecting. You will also be asked to find the domain and range on a lot of these problems. So again, the domain is how far to the left the graph goes, how far to the right. In this case, it goes as far to the left as 0. It is limited. It doesn't go all the way to the left. It only gets as far to the left as x equals 0, but it does go forever to the right. So the domain is 0 to infinity. The range, again, we find that from the graph by asking ourselves how far down does the graph go, how far up does it go. And it goes down forever. It's not limited in how far down it will go. It keeps going to the right forever, and it's heading down as it does that. But it is limited in how far up it will go. It only goes up as high as y equals 0. So the range will be -infinity to 0. So these will be our domain and range.